All right, so here we're going to start taking a look at oxidation and reduction reactions, which are affectionately known as redox reactions. So the reason the name has both oxidation and reduction in it is because we must have both at once. You can never have only an oxidation or only a reduction. You've always got to have both together inside of your chemical reaction. So let's take a look at our first problem here. So here we have 2 calcium plus O2 going on to 2 CaO. And there's a note here that says redox reaction always involve an electron transfer. So another way to say that is we will always have elements changing their charge. That is the hallmark of a redox reaction, and that is one way to recognize that you're looking at a redox reaction. All right, so now I'm going to separate my elements. So I'm going to start with the calcium here on the left. And that calcium has no charge. It is neutral, so I'm going to go ahead and put a 0 there. We're going to talk about our rules on how to determine our charges or oxidation states in just a moment. But for now, if you see an element all by itself and it has no charge listed, you're going to assume that that charge is 0, that it is neutral. So I'm going to have my 2 calcium over here, and they have no charge. Now I'm going to write my reaction arrow, and on the other side we have a ionic compound. And within an ionic compound, our elements do have charges. So calcium is a predictable ion, and way back in your nomenclature days, you learned that calcium was a +2 and oxygen was a -2. So here I'm going to say that it is 2Ca2+. So we've taken our 2 neutral calcium and we've turned them into calcium 2+. So from neutral into an ion. All right, next up we're going to look at our oxygen, O2. And again, it's an element all by itself, and we have no indication that it's an ion. There's no charge listed, so we are going to assume it is neutral. So I'm going to put that 0 up near the top. All right, now on the right-hand side, I have the oxygen that's from the ionic compound, which we know to be a 2-. So I'm going to say we have 2O2- here. So here we have 2 elements that have both changed their charge, which is what we expect for our redox reactions. So now let's take a look at that calcium right up at the top. So a calcium went from a 0 to a 2+. So the only way that it can become positive is to lose some electrons. And here what I'm going to say is it lost 4 electrons. And if you're wondering why 4 electrons, if it's a 2+, the reason is that we have 2 calciums. Each of them lose 2 electrons, and that's where the 4 comes from. All right, next up, we have our oxygen. So oxygen have gained electrons. That's the only way something neutral becomes negative. And I'm going to say that they have gained 4 electrons. And the way I got 4 electrons is that we have 2 oxygens, and each one has a 2 negative charge. So 2 times 2 gives me 4. All right. So now we've got to decide which one is an oxidation, which one is a reduction. All right, so here are our rules. So the first one says oxidation is the loss of electrons, and that is often known as oil. And oil stands for oxidation is loss. All right, then we have reduction, and reduction is the gain of electrons. And so we often call that Rig, and that is reduction is gain. So the way students often remember this is oil, Rig. Now I'm going to show you another way that I think is easier, but this is the way that most of you learned it if you took Intro to Chem. So I want to start off by using the format you're familiar with. So if we say oxidation is loss, and we look at who lost electrons, it was calcium. These electrons have been lost. Therefore, this is an oxidation. And reduction is gain. And we look at who gained electrons, and that was oxygen. So this we're going to call our reduction. All right, so I told you I would show you another way as well. This way works perfectly fine, but I do think the other way is a little easier. All right, so the other way involves looking at the charges. So oxygen went from a 0 to a 2 minus. So if you're in math class and you're looking at the number line, from 0 to 2 minus, that is a reduction. The charge was reduced, and therefore we say this is a reduction. So simply based on the charges, based on those numbers from 0 to -2, that is a reduction numerically, and therefore it's a reduction in chemistry. Now for calcium, it went from a 0 to a +2, so it was a gain in that charge, or what we'll soon call oxidation number. And for a gain, we're going to call it oxidation. So let me write out this method that I've been talking about. So in terms of this method, a reduction is when the charge or oxidation number, which we're going to talk about in just a minute, gets smaller. And another way of saying gets smaller is it is reduced. All right. So next up, let's talk about the reduction. Next up, let's talk about the oxidation. So in oxidation, is when the charge or oxidation number gets bigger or gets larger. So if it gets numerically larger, that's what we'll call an oxidation. Let me clean up my writing here. All right, so this is just another method. So if you are happy with the oil rig method, of course, please use it. I do find this easier because I don't have to think about who's gained electrons, who's lost electrons. I just simply look at those charges and say, hey, whose charge was reduced? Whose charge got smaller? Well, that's my reduction. And whose charge got larger? Well, that's the oxidation. So this is just an alternative method. Again, if you don't like this method, you do not have to use it. Oops. All right, so I've been throwing around that word oxidation number, and now I want to go over it with you officially. So back when we did ionic compounds, we talked about charges. But for redox, we really need to assign a charge to everything, even things that don't really have a charge of their own. So we have molecules that have no charge, but we've got to track their electrons. And so in order to do that, we pretend they're ionic and we start assigning oxidation numbers. So we're going to go through some rules, and the first one says an element in its elemental form. So this is the form that it would be in just by itself. So it has an oxidation number of 0. So you could think of that as a charge of 0. So all of these down at the bottom, this is the way we would normally find them. So O2, H2, neon, mercury is a liquid, calcium is a solid. This is the way they are naturally. And if you see an element just by itself, the way it is naturally, we will assume it to have a charge or oxidation number of 0. And that is how in the previous example I found that the calcium had a charge or oxidation number of 0, and so did the oxygen. It's because they were in what we call their elemental form. It is the way that we would find them in nature, and they're all by themselves. The reason that our products right over here were not neutral is because you have 2 of them together, and so that made it an ionic compound. But when you have them all alone and they do not have any charge written next to them, then we're going to assume that they are neutral. All right, so next up, assigning oxidation numbers. So here's our second rule, and that is a monatomic ion, the oxidation number is the charge. So if you have one element all by itself in its ion form, that charge that you see, that is the oxidation number. So whether it's a predictable charge like sodium or oxygen, or whether it's an unpredictable one like chromium or iron, if you see an element all by itself, and that's what we mean by monatomic, mon coming from mono, meaning just one. So one element all by itself, and it says, hey, I'm a sodium ion, I'm a 2+, that charge is the same as its oxidation number. All right, so here's a little bit about our oxidation numbers. So assigning oxidation numbers is a way of keeping track of our electrons. The difference between an oxidation number and a charge is that sometimes we have to assign this oxidation number to something that doesn't actually have a charge. So we are giving average values, not actual values. So when we say sulfur might have an oxidation number of +4, that's not a real charge. That really is an oxidation number because sulfur may not actually have that charge. There are certain things that do. For instance, these are all charged ions. The charge is the same as the oxidation number. However, with oxidation numbers, we will be assigning a number to a neutral element within a molecule. So there are times where we give something an oxidation number where it doesn't really have a charge, and we'll take a look at some of those. But I just want to give you an idea of what we're doing here. We are treating everything as if it's an ionic compound, even if it's not. But if it is an ionic compound, that's when our charge and our oxidation numbers are the same. All right, so here are some rules. And first off, oxygen is usually a -2. Now, sometimes it can take on a -1 if it's peroxide, but what I'm going to tell you is most of the time it's a -2. So treat it like it's a -2 unless you have a good reason to suspect it's not. Hydrogen, likewise, is going to be a +1 most of the time. There is a time where it could be a -1, but I'm going to tell you to treat it as a +1 unless you have a good reason not to. Fluorine will always take the -1, and the other halogens will usually be -1. However, sometimes they can change oxidation states, especially if they're bonded to oxygen. But what I'm going to tell you for now is treat them as if they have a -1 unless you have a good reason not to. All right, finally, the sum of all the oxidation numbers will equal 0 if you have a neutral compound, or the charge of the ion if it's a polyatomic ion. So we're going to go through some examples here, and it makes a lot more sense when you see it in action. I know the rules are kind of ugly, not as beautiful as they could be, but it makes more sense once we do some examples. All right, so the first one we're going to look at is NaCl. So NaCl is an ionic compound. So we know sodium predictably forms a +1 charge, and we know that chloride predictably forms a -1 charge. So because of that, I am going to say that sodium has an oxidation number of +1 and chloride has an oxidation number of -1. So again, if you have an ionic compound or an ion, you already know the oxidation number. It's the same as the charge. Where things get a little tricky is when we have a molecule. So the one I just underlined here, SCl2, that is a molecule, and there technically aren't any charges, but that's okay. We're going to assign it charges because we've got to figure out where the electrons are going, and the only way we can do that is by assigning those oxidation numbers. So it's not a true charge. That one will be an oxidation number. So let's take a look at our SCl2. You might remember from our nomenclature days, that's sulfur dichloride. What I'm going to do is I'm going to write out the sulfur and the 2 chlorides. All right, so what our rule said is for halogens, you're going to assume it to be -1 unless you have good evidence not to. So I'm going to go ahead and assume these are -1s. I don't know what sulfur is, so I'm going to call it an X. Now notice there's no charge up here. Because there's no charge, I'm going to assume this to be 0. So this will equal 0 unless you see a charge, unless it is an ion. All right, so from here, we just write this out like an algebra equation. X minus 1 equals 0. And so if we solve for x, we'll get x equals plus 2. So here, I'm going to write out my oxidation numbers. And I'm going to say sulfur is a plus 2 and chlorine is a negative 1. Now sometimes students ask, well, hey, what if I've got 2 that I'm not sure about? And what I'm going to promise you is in these kinds of problems, you'll only get 1 that you have to figure out. The rest of them will all be their predictable charge or oxidation number. All right, so I'm going to copy this and bring this up. Oops. All right, so that was our sulfur dichloride. Next up we have sulfate. So this is a polyatomic ion, but we need to know about the elements within it. So SO4 2-. So I'm going to separate these, and I'm going to say sulfur. Now there's 4 oxygens, and I could write these out, 1, 2, 3, 4. But when we have a whole bunch like that, sometimes multiplication is just the easier way to go. And I'm going to say 4 times oxygen, because we really have 4 of those oxygens. All right. So sulfur, we don't know about, so I'm going to put an X here. Now oxygen we do know about. So I told you to assume it's a negative 2 unless you have good evidence to assume it's something else. So I'm going to say 4 times negative 2. And here I'm going to say that it's equal to negative 2. The reason, oops, sorry about that. The reason that it's equal to negative 2 is because of this negative 2 right here. All right, so again, if there's a charge listed, that means you've got an ion. It needs to be what everything equals. But if we go back to the previous problem, notice there was no charge listed, so we assumed it to be 0. All right, so let's set this up. So we have X, and then we have negative 8. So 4 times negative 2 gives us negative 8. Altogether, that is a negative 2. If I add 8 to both sides, it looks like X is plus 6. So sulfur is a little bit notorious because it can change its charge, just like our elements in the transition metals. Earlier, we said sulfur had a plus 2 oxidation number. Now we're saying it has a plus 6 oxidation number. But let's go ahead and write out our oxidation numbers here. All right, so we said sulfur was plus 6 and oxygen was a negative 2. So I hope this is making sense how to find our oxidation numbers. So we want to set it up just like an algebra equation. So there's only going to be one element that you don't know the oxidation number for. You'll know all the other elements, and you'll always know what it equals. So if it's an ion and has a charge over here, charge over here, you'll set it equal to that charge. If it is a molecule, if there's no charge, which would be evidenced by having no charge right up here, then you'd put a 0. All right, so let me copy this up to our PowerPoint. All right, so next up, we have sodium sulfite. And there's a couple different ways I'm going to show you how to do sodium sulfite. So this is Na2SO3. So the first way we're going to do it is just the way we've done it in the past. So I'm going to say we have 2 of our sodium, and we have 1 sulfur, and we have 3 of our oxygens. So sodium is a predictable ion. We always know its charge, and that is a plus 1. So we have 2 times that plus 1, and I'm going to add in X, which we don't know. And then we'll have 3 times oxygen, and oxygen also has a predictable charge of -2. All right, then when we try to figure out what it's equal to, we look right over here. Since there is no charge listed, we're going to assume that charge to be a 0. So one more time, if there is nothing over here, and let me get rid of this blue line so it doesn't confuse us, there's nothing listed there, then we assume that it equals to 0. All right, so from here we're just going to solve the algebra. So 2 times 1 is 2 plus x, and 3 times a -2 will give us -6 equals 0. And so then if we combine here, we have x minus 4 equals 0, and then if I move the 4 over, x equals 4, and that is a positive 4. Now for oxidation numbers, it is customary to write in the positive charge, but you do not have to. So if you don't write any charge, I'm going to assume it's positive. But again, if you're looking at it in textbooks or on the internet, it's just customary to have that positive there. All right, so now we know our sulfur charge, and we already knew our sodium and oxygen, so let's write out what we've got. So these are oxidation numbers. So we said sodium is a +1, comes from its predictable charge. Sulfur is a +4, and that came from the equation we set up and solved for x. And then oxygen is a -2. All right, so let's go ahead and copy this over. All right, so next up, I want to show you an alternative method. Both methods are good. I don't know if one really saves you any time over the other. It's just some people have a preference for one or the other. So I'm going to call this one method 1, and we'll call the other one method 2. All right, so we're still looking at sodium sulfite. Now, for some people, they look at that and they immediately know that this is an ionic compound. So in their head, they're going to break this up and say, hey, I know this is 2 sodiums plus a sulfite that looks like so. If you're one of those people where that sodium just screams out at you, hey, I already know what I am, I'm a 1+, you can leave that sodium by itself, and then you can deal only with the sulfite. So now I'm going to progress and only deal with the sulfite. And now what we'll do is we'll take our sulfur and 3 oxygens. So we don't know what sulfur is, so I'll put an X. And then I know I have 3 oxygens, so 3 times -2 equals, and in this case, it is going to equal a -2 because this is now an ion. So I have to match what it's equal to its charge. All right, so just to solve this out, we got x plus -6 equals -2. If I add 6 to both sides, it looks like x is equal to a +4. So we have our sulfur with an oxidation number of 4. We have our oxygen with an oxidation number of -2. And we have our sodium with an oxidation number of -1. Let me go ahead and write that out. So we said sulfur was a +4, oxygen was a -2, and our sodium was a +1. So that's exactly what we got with the other method. So again, neither of these methods are better or worse. They're just 2 different methods. Feel free to use either one. All right, so I think I'm going to break the video here just so they're in shorter, kind of more bite-sized chunks, and then I will continue on the next video.